guys forgot the abbreviation of MPP. Why don't you search the Google? MPP means? The SMP is the symmetric multiple process. MPP is? What is that? Massive. Massive. The parallel. The P is the parallel process. So MPP architecture, massively the parallel processing is shared only disk or even shared nothing. So the problem is you cannot share the data along the node, along the CPU. So to address that one, Newman architecture is from IBM. It will take a time, but I need to access the cache data, memory data in the another node. At that time, it will be slow. So when you design your program, try to independent, but not always is hardly independent, perfectly independent. In that case, you need to share. So you are going to access the memory in another CPU. It will be slower. That is called the Newman architecture. It was very popular, still used in the computing environment. Then when you think about such a thing, the CPU scheduling will address the issue of the software affinity, hardware affinity. It can be hardware affinity, but it can still access the data in the other. Also, definitely, as I said, it should be load balance. When you balance the load, which means we have the two CPU over here, CPU 1 and CPU 2. If this one is busy, we need to utilize another one. At the time, two approaches. One is the pooling is you can take out, okay? From from the CPU, which is idle, then the pull out the job. So I'm not busy, so please give me a job. Okay, so that is the pulling. Another approach is pushing. If you believe the one processor is busy, then the push out the job too. So you can utilize such a push and pull migration to do that. So that is a multiple processor. It's much more complicated. I just raised the simple issues of the multi-processor scheduling algorithm, but there is another advanced level operating system for the parallel, the distributed operating system. At the time, you can consider the details of the scheduling for the multiple processor. What about the multi-core? Multi-core is basically the same thing, but what is a core? What is the difference between the multi-core and the multi-processor? What is the difference? Multi-core and multi-processor. Common thing is they can process a number of threads at the same time. That's the common thing. What is the difference? Multi-core has how many chips? Only one board, one chip, then multiple CPU inside. But the multi-processor is a separate the chip. So you can add one CPU, another CPU, and so on. What is the benefit of the multi-core? Because it's on board, the same board, it may be faster to communicate. That's the speed, efficiency. Another one is sometimes easily ignore this part. It's the power. You can save the power. One of the biggest problem of the design and managing and using the CPU processor is the power. So if you run the heavy program, probably it will be noisy because of the fan. It's a cooling system. Any laptop or any computer system, it's a cooling system is very important. Otherwise, it will be the hardware damage. Think about why Google, Amazon, and Facebook, they make the data center on the Sweden or the Iceland or such an area. Cold. It's a cheap, so it's a cold temperature. Nature, it can be automatically cooling down. Definitely, inside the data center, they have something system for the consistent temperature, consistent humidity level. Okay? So why? Because computer need the CPU. Definitely CPU is the most important. CPU generate a lot of heat. So heat is the biggest problem. You need to cooling down. Also, heat means it's energy. Energy comes from power. So reducing the power is very, very important. So when you are using dual core, it's one chip, so you can optimize it easily, such as the power consumption. That's another interesting. Probably I mentioned. I'm not sure. One of my friend. Actually, this funny is we graduate the same elementary school, 1983. Then we never met each other. Then suddenly, several years ago, in one of the conferences in New York, we met. Then we easily recognize each other because his shape is really the unique, the face shape. So after 30 years, it's not changed. Also, my friend recognized me easily because my voice is never changed. So my voice is a little bit husky voice because I yelled a lot when I was a kid, and so it's still the same issue. But anyway, his job, he's still the IBM. He's in the IBM, but he was in the Austin. In Austin, you probably know the electrical engineering student. No, the Austin is popular for what? Texas Instrument and semiconductor is a hardware. So Austin has the semiconductor company Samsung and the IBM and so on, such a hardware company, especially the semiconductor company. So he was architect design of the power chip of IBM CPU. So he was designer, chip designer for the CPU, but he moved to the White Plains, the IBM TJ Watt Center, because he lost the job, his position, because IBM decided they give up all hardware part. They sell all the hardware part. Then they do not give up. IBM does not give up their employee. Instead, he was assigned to the civil engineering part to design the power grid in the city, like the Manhattan, how to optimize the power supply, power grid. Because chip design, one of the important factor is how to reduce the power consumption, how to optimize. So if you see the kind of design of the chip, it's very similar as the CD design. Then which one is nearby, which one is not, which one is supply, which one is chain. So that is exactly, he said, same as he designed for the CD. So in terms of power. So he works for the data analytics team. So he applied the data analytics data, the machine learning, to optimize the power, the consumption like that. Think about your future also. So that's the kind of example. So multi-core, so we actually try to save the power. So then it may be easier than the multiprocessor. But still, the operating system level, they need to consider because it's logically one. The next one is the real-time CPU scheduling. Have you ever heard about the real-time processing? Real-time, the computer, real-time? Probably, yes. What is the real-time? Same time. Same time. Anyone? Is it possible, really real time?
No.
It's not possible. Then why do you say the real time? It's the fast? So how much fast? 0.1 second. It's very slow in terms of CPU clock speed. The millisecond, nowadays nanosecond. So fast, we know what is a real time means, but it's not easy to clearly define what is a really real-time processing, or real-time computing, or real-time whatever. So real-time actually is not only just fast. Instead, it's a guaranteed. Guaranteed means what? For example, several years ago, in Japan, what happened around the Fukushima? Anyone? There's an earthquake, so there was a tsunami. Then the power plant, the nuclear power plant, actually the burned. So that caused a huge issue. Then they probably have the alarm system in case of something, the tsunami or then they need a very fast the system, fast response time system. But probably they have something within 10 seconds should be alarm, then within 5 minutes they can evacuate the person nearby, something like that. That time is the kind of guaranteed, okay, deadline. So when we are talking about the real time, intuitively we expect a fast, but not only just a fast, but it's a guaranteed, meet the deadline. So if we think about the first come first serve or any other CPU scheduling time, we cannot guarantee this one is a faster overall, better than this one. Okay, so shortest remaining job first is faster, but we cannot guarantee always fast. Depending on the situation, it may be slower. That may not be applicable for critical system like the nuclear power or some of the device need when we touch, it should start within 1 second. Otherwise, nobody will use. It may take the 10 seconds to schedule the starting the recording. It will not be used. So within certain amount of time, something deadline should be processed. That is the real time. So in case when we talk about the real time CPU scheduling, means intuitively fast, but more important thing is whether each process meet the deadline or not. So that is the real-time CPU scheduling. There are two types of the scheduling. One is soft and another one is hard. Soft means it's a flexible, which means try to my best to meet the deadline, but maybe not sometimes. That is a soft real-time. Hard real-time should must, otherwise it's all failed. So soft real-time may be used not very critical system. However, why the hard real-time is very, very important. So it's like the nuclear power alarm system. So or something driver risk car. Driver risk car response time should be guaranteed. Otherwise, it hit the object or the other, so it will kill the person. So it should be hard, the scheduling. So getting more important in embedded system. A lot of embedded system we have like the wearable device or IoT that should have the scheduling like the real time, the scheduling. Some of them like the for fun or the toy style that can be solved to real time, but related to healthcare like something echocardiogram, then the send the alarm, that should be the hard, the real-time system. So at that time, the issue is there are latency. Latency means it's a delayed time. There are two types of latency. One is currently the modern operating system is based on what? Interrupt. So what is the interrupt? Interrupt is the signal. So I have something. So I'd like to send my data to the CPU. Then the operating system stop. It's really stop. Interrupt. And wait. The signal from the disk controls, then I can send it. Then the memory receive such a data. That's the interrupt. So which means during the interrupt, nothing you can do. It's called the latency. So we have the interrupt latency. Then interrupt. Then what happened? Operating system run scheduling algorithm. Then assign this process is this processor. Okay. Then it will be context switch and run. During that time also it's nothing going on. So it's another latency is the dispatch latency. So we cannot avoid such a interrupt latency and dispatch latency. Because of that, there is no really real time the scheduling algorithm. It's guaranteed. Then after that, so we are going to consider the period. So let's say this is the CPU time, and this is the amount of CPU burst time for the process. Okay, this process needs this one. Then this is the deadline. So this one should be done within this deadline. then we will consider CPU time as a periodic. You can use the CPU cycle, or you can use something fixed amount of time as a period. Like 5 milliseconds is a period. Within 5 milliseconds, deadline should be less than such a period. Okay? So like for example 4, then the CPU burst time 2, which means this process should be done within 4 milliseconds inside one period. So this is called the real-time processing, real-time operating system. So the operating system that has the real-time scheduling is called the real-time operating system or real-time system. Okay, then let's see what is the example of such a real-time. So first approach is we are going to consider the period. Shorter period, which means so we have two, the student. His due is within 5 seconds. And another student is 5 hours and 10 hours. Which one is more important? This one. So because it's quickly approaching. So shorter period is a higher priority. So we will select the process that has the shorter period. And the longer period is we can consider as the lower priority. So that's the P1 deadline here. P1 is the deadline is every 50 milliseconds. P1 100, P1 here, and P1 here. And P2 is the period is every 100, 100, 100, which means P1 is always higher priority. Okay? So, for example, first time P1 will be selected. So within period it's done. So it's done. So then the P2 will be selected. Then even P2 has the total 35. The CPU burst time. It's not done yet, but at time 50, new period of P1 is started, which means P1 is important. So P1 will be selected again. So P1 is done. Then the P2 will be processed. Why? P2, the period is end the 100. Still have a time. So we can select always a P1 because it has a shorter period time, shorter deadline. So that is the rate monotonic scheduling. So we are going to consider such a period or deadline of the P1 and deadline of the process, shorter deadline, shorter period, higher priority. Okay, that makes sense. So then we can select the process that approaches the deadline. However, in this case, let's say the P1's deadline is 50, P2 is 80. Okay? That may be possible. We change the deadline of P2. So P1 is selected, it's done, and P2 is selected. It's not done yet because it needs 5 more and 10 more, but P1 will be selected at this time because P1's deadline is 50, P2 is 80, so P1 is shorter. So P1 will be selected. Because of that, P2 will not be completed. Okay, sometimes if we just use the deadline first, it may be problem. So, however, if we switch P1 and P2, like the P2 first, P1, there might be no problem. Because the P1, the new deadline is 100. So P1 can be done after P2. So to consider earliest deadline for each time, earliest deadline we will consider. Like for example, at this moment, earliest deadline is the P2 is here, P1 is here. So P1 will be selected. It's like the what? Shortest job first, shortest remaining job first. Whether we consider the current status of the process for regarding to the deadline. Okay, so this is the one of the examples. There are a lot. It's a still open problem because it's not possible really real time. Problem is how much reduce, how to guarantee the such a scheduling. So it's still used. And also, as I said, the scheduling algorithms should be very light. It's not a complicated one. It's every time it's running. in your the system. Think about the embedded system. So this one has the device IoT and connected, which means should have the scheduling. So, but if it takes a time to run that scheduling, sometimes you stop your music, so you cannot hear the music, without stopping. So that the scheduling algorithm nowadays used a lot for such an embedded system. Okay. Then there are the others are the example. We have the still time. So this is a POSIX example for the real-time scheduling. So like the policy is a scheduling it's a round robin, and the first in first people we can use that. Okay, so we will very quickly see the example of the operating system. What kind of the scheduling algorithm are used for the popular this one, the Linux and the Windows. The Solaris. Solaris was popular in our mid-sized server, but not nowadays a lot. So up to the version 2.5. What is the version 2.5? If you are using Android phone, each version has something name. Gingerbread. What is the current one? Lollipop and so on. What is the current name of? Really? I never used. Mine is still the lollipop. I'm not sure. So, however, if you take a look at the version number, it is 4 point something and something 5 point something. And also, if you take a look at kernel version, it's a 2 point something. Actually, Android is starting from such a same the Linux kernel. Okay, so then 2.5, 2 point something means it's kernel version. So up to the 2.5, they use something the same, because the idea of Linux is Unix was not free open source the operating system. Instead, you need to pay. Anyway, you need to pay for the Unix operating system. So Linux is kind of the mimicking Unix system with a free open source. So they first copy the algorithm of the Unix a lot. So up to the 2.5 is just a kind of variation. Some of them are not very optimized because it's kind of the free purpose and open source purpose, not commercial purpose. They don't care such a performance. So it's just copy. But from the version 2.5, they focus on the performance. So they try to O of 1 scheduling algorithm. What does it mean? O of 1. What is O first? I believe that you learned this in your freshman, right? In your freshman, the introduction of computing or introduction of data structure you learn is the big O notation. So what is the big O notation? For time complexity, to represent how much complex of your algorithm. Okay? So then, what will be the value of a big O notation? You will take highest power of the item. For example, linear ax plus b is in terms of big O notation 1 over what? Over n. It's a linear, means when you have the more input, it will be linearly increased. Still good. Actually not faster, because the more data you have, the longer time. Okay? So ideally, it's O of 1. O of 1 means no matter how many data, how many input, how many processes you have, it will be constant, which is the very good, almost best. But not many O of 1, the algorithm we have. Instead, logarithm. The more data, the longer time, but it's not like the linear, it's like this. Okay? The worst case, n squared, and so exponentially is increased. Sorting algorithm, we focus on n log n. And if you have the n, it's better, something like that. So O of n is, it doesn't matter how many processes are running, it's a guaranteed time. It's a real-time scheduling. So that is the O of n means it's a real time. Okay, they said that it's a nice value. Nice value is kind of priority. So they use both. Most of the current operating system use a priority base. Okay. Then so from the 2.6 is called the completely fair scheduler. It's not really completely, but name is completely. They said it's a fair. The processing is called the CFS. So they are based on, many of them are based on, to be fair, which algorithm is the best one? Round robin. So they use the round robin to be fair, the scheduling algorithm, and the priority and the round robin. Windows. Can you guess what kind of the CPU scheduling algorithm is the primary algorithm in Windows? If you go to the task manager and right click, you can change priority, real time, normal, and something like that. Windows use a priority base. Then they have the such a 1 to 15, 16, 32 different level of the priority. Okay? So priority 0 is the memory management thread, which means it's the fastest one. And the other is 1 through 32 different level of. But we usually, in the API, Windows API, we use, so you have seen the such a thing, real time, high priority, normal priority, idle, and so on. So this, the name, this group of priority will be used for the scheduling algorithm. So this is an example of the something such a number. Okay, so I'm going to skip the Solaris. Then, mostly we discuss about, so far we discuss about the most of the such algorithm. Then, once we have the, for example, I have an idea, okay? It's a better, the response time, the CPU scheduling algorithm. Then, how can you claim your algorithm is better than the other? You need to publish. Then, when you publish, you need to prove your algorithm is better than the other. How can you prove? Best way? It's the same thing for any research. If you are interested in the master thesis or the PhD, so you need to know this. So when you have the new idea, new algorithm, what is the best way to prove? Anyone? Mathematics. Okay, if you can prove using the mathematical equation, like the theorem or corollary or anyway, that's it. You don't have to code. You don't have to implement. Sometimes if you take a look at the computer science textbook, you can see only math equation, no code. Coding is one of the way to use for the computer, to communicate with the computer. Algorithm itself, you don't need if you can prove using the mathematics. So the higher the level of the textbook, they use only the equation, so mathematics. But not always that's true. So there are several different ways to prove the idea. One of them is first, deterministic modeling. Deterministic modeling means it's we for a given determined the data. For example, process state P1 alive time 0 with the CPU burst time 5. P2 alive this and P3. Then test with the existing algorithm, first come first serve. And Judy stuff first. And my algorithm, which one has lower waiting time? Which one has the lower response time? If mine is lower, then which means mine is better. But at that time, you should be careful what kind of data. So there exists a benchmarking data set. Benchmarking data set is commonly used. So I have an idea, so I develop, it looks like better, so I manipulate. So some of the data fit to my algorithm only. But it's not generally, so which will not be accepted. So usually the benchmarking or the reasonable, you should show how to create, how to collect such a data. It's the same thing for the machine learning or data mining or data analytics. You need to prove such a data. Using such a data, you can model. Yeah. Queuing model. Queuing. What is the queuing here? How many queue? So we can understand such a problem. Not only CPU scheduling algorithm, many other algorithms. There's an input and there is an output, right? How many output? How fast the output is? If we can model the x-axis is the input and y-axis is something value like the waiting time or response time, then we can model using statistics like the distribution, like whether this is a Gaussian distribution, whether this is a Poisson distribution, whether this is the chi-square distribution. We are going to model input and output using statistics. This is called the queuing theory. Which area of computer science is used a lot, such a queuing theory? What subject of computer science? One of core subject. Networks. Network is always sender and receiver. Input and output. So if you have a bottleneck, output will be slower. Okay? Lower response, the higher response time and so on. So it's using queuing theory. Network was designed and proposed and so on. So queuing theory. You probably heard about such a queuing theory example, like the McDonald's. So one of the very popular project is you can sit on the entrance door of the McDonald's and check the entrance time of the customer. Then how many of them are check the register and the order? How long it takes? Sometimes if there's only the McDonald's employee, it takes a long queue. So you can design model, and a certain time you don't need to hire the part-time. So to decide the optimal number of the employee, you can check the input and output. You can design actually queuing theory, so you can check. So it's like this one. It's a Poisson distribution, skewed distribution. Then third one is measurement from the implementation. Means you implement actually the algorithm. Your algorithm implement the first come first serve, then measure the performance. That is another way. The last one is, why don't we implement a computer system that include your scheduling algorithm? That is perfect, right? If this computer is running fast, then this one is the best one. Problem? It costs and a lot time consuming, sometimes not realistic. Think about I developed the algorithm, so I developed the computer and the operating system. If that doesn't work very well, you need to throw away. So it costs and takes some time. That is the real implementation of it. So that is the how to evaluate implementation. Let me show you the one example of the CPU scheduling.